For the introduction, a time-varying field refers to an electromagnetic field whose properties change with time. It is a fundamental concept in electromagnetism, and the behavior of such fields is described in Maxwell's equations. Maxwell's equations are a set of fundamental equations in classical electrodynamics that describe the behavior of electric and magnetic fields. In this chapter, there are two major concepts. First is electromotive force and second is displacement currents. Faraday's law. Faraday's experiment shows static magnetic fields do not cause current flow, but time-varying fields cause voltage in closed circuits. Faraday discovered that induced EMF in closed circuits equals the time rate of magnetic flux change. The formula to find voltage EMF is equal to negative n d psi over dt, where n is the number of turns and psi is the flux of through each turn. As for Lenz's law states that current flow direction in a circuit opposes the change in original magnetic field due to its induced magnetic field. Based on the figure 1, a circuit showing EMF producing field EF and electrostatic field EE. The total electric field can be expressed as E equal to EF plus EE. If we integrate over the closed circuit, we will get an equation like this, where EF and EE are equal to opposite within the battery. It's important to know that electrostatic field EE can maintain a steady current in a closed circuit, and EMF produced field EF is non-conservative. Voltage and potential difference are usually not equivalent.
So now let's discuss about the transformer and motional electromotive forces. This is about the connection between electromotive force and electric field. Through Faraday's law, we can explore the relation between electric and magnetic field. For a circuit with a single conductor which is n equal to 1, the equation will be induced voltage is equal to rate of change of magnetic flux through the circuit. This equation, also known as Lenz's law, in terms of E and B, the equation can be written as integral of E dot dl around a loop is equal to the negative time derivative of the total flux through the loop. Note that negative sign in this equation means that the induced voltage will create a magnetic flux that is in opposite direction from the change in applied flux. The three ways of induced electromotive forces are by having a stationary loop in a time-varying B field, second by having a time-varying loop area in a static B field, third by having a time-varying loop area in a time-varying B field. So now we consider a stationary conducting loop in a time-varying magnetic B field. The equation becomes V EMF is equal to integral of E dot dl is equal to negative of integral dB over dt ds. This EMF is induced by time-varying current in a stationary loop is often referred to as transformer EMF in power analysis, since it is due to the transformer action. By applying Stokes' theorem to the middle term, we get this equation, which del across E is equal to negative dB over dt. This shows that the time-varying E field is not conservative.
Bismillahirrahmanirrahim. My name is Muhammad Arif Nasrullah bin Muhammad Kisharin. We continue this presentation still on the transformer electromotive force. Next, we move to moving loop in static B field. When a conducting loop is moving in a static B field, an EMF is induced in the loop. So, the force on the charge moving with uniform velocity U on a magnetic field B is Fm is equal to Q times V. So, the motional electric field is EM, as EM is equal to Fm divided by Q or U times V. If we consider a conducting loop moving with velocity U as consisting of a large number of free electrons, the EMF induced in the loop is VEF is equal to integrate of EM times V dl or integrate U times V times V dl. This type of EMF is called motivational EMF or flux cutting EMF. It is kind of EMF found in electrical machines such as motor, generator, and alternators. Next, we look for another situation. It is where a rod is moving between a pair of rays. In this example, P and U are perpendicular, so the equation will be Fm is equal to ILB and VEMF is equal to UBL. By applying the Stokes theorem, we have integrate of V times VEM times VDS equal to integrate of V times U times V dot times DS or V times EM is equal to V times U times B. Lastly, we move to moving loop in time varying field. In the general case, a moving conducting loop is in time varying magnetic field. Both transformer EMF and rotational EMF are present. So, the total EMF is VEMF is equal to integrate of E dot dl is equal to negative integrate of dB over dt times VDS plus integrate of U times B times VDL or V times B is equal to negative dB over dt plus V times VU times VB. So, for the summary of Maxwell equation in final forms, Maxwell equations in their final form describe the fundamental laws of classical electromagnetism. They are a set of 4 partial differential equations that relate the electric and magnetic field to their sources. First is Gauss' law for electric field. Vd is equal to PV. Second is Gauss' law for magnetic field. V times Vb is equal to 0. Third is Faraday's law of electromagnetic induction. V times Ve is equal to negative dB over dt. And lastly is Ampere's law with Maxwell addition. It is V times B is equal to Uj plus Ue times V dE over dt.
Okay, so I will explain about the particle charge in electric field and magnetic field. Electric charge create an electric field that can attract other charged particle via a force. Charged particle in electric force have their direction. Proton experience force along electric field line, but electron experience force opposite to electric field line. The equation F equal to QE is explain the force experienced by charged particle in electric field. Charged particle can be stimulated to move faster due to electric field. Let's move to the magnetic field. Magnetic field generate force on charged particle by moving electric charge or magnet. Charged particle in magnetic field experience force perpendicular to velocity and direction affecting in motion. The formula F equal to VQB sin theta is explained about the force experienced by charged particle in magnetic field. Charged particle move along magnetic field line in circular pattern without changing their speed. The magnetic force can be used to deflect charged particle. So let's move to the application. The application we have 5: radio wave, microwave, infrared radiation visible light, X-ray, gamma ray.